Potential difference in a uniform electric field. In this session, we will explore the behavior of electric potential within a uniform electric field. We will start by defining the potential difference in these specific fields and examining the mathematical relationship between the electric field vector and the scalar potential. From there, we will discuss how charged particles move under these conditions and conclude by looking at equipotential surfaces, which are regions where the potential remains constant. This foundation is essential for understanding how energy is managed in electrical systems. While the general equations for potential difference apply to any electric field, they become much simpler when the field is uniform. Let us consider a uniform electric field, E, directed along the negative y-axis. To find the potential difference, delta V, between 2 points A and B, we integrate the dot product of the electric field and the displacement vector, ds. Since the field is uniform, its magnitude E is constant and can be moved outside the integral. If the displacement is parallel to the field lines, the angle is 0, and the integral simply becomes the product of the field magnitude and the separation distance would. Thus, we arrive at the simplified expression, delta V equals negative E times D. The negative sign in our equation, delta V equals negative ed, carries an important physical meaning. It tells us that the potential at point B is lower than at point A. This leads us to a fundamental rule in electromagnetism. Electric field lines always point in the direction of decreasing electric potential. Think of it like a stream flowing downhill. If you move in the same direction as the electric field, you are moving toward a lower potential. Conversely, if you move against the field lines, you experience a positive potential difference of ed. For a positive test charge moving from A to B, this transition results in a decrease in the electric potential energy of the charge field system. We can better understand electric potential by using a gravitational analogy. Just as an object with mass, m, in a gravitational field, g, has potential energy based on its height, a charge q in an electric field E has electric potential energy. The change in this energy, delta U, is equal to the charge multiplied by the potential difference, or negative QED. For a positive charge moving in the direction of the field, the potential energy decreases, much like a ball falling toward the ground. In both cases, the system naturally tends to move toward a state of lower potential energy, converting that stored energy into kinetic energy as the particle accelerates. Now let us consider the more general case, where the displacement vector s is not parallel to the electric field lines, but sits at an angle theta. Here, the potential difference is determined by the dot product of the electric field vector E and the displacement vector s. Mathematically, this is delta V equals negative E dot s. This tells us that only the component of displacement parallel to the field lines contributes to a change in potential. Consequently, if we look at point C, which is located directly below point B but horizontal to point A, we find that any displacement perpendicular to the field lines results in a dot product of 0. This means that points B and C, which lie on a plane perpendicular to the field, are at the exact same electric potential. This leads us to the concept of equipotential surfaces. An equipotential surface is a continuous distribution of points that all share the same electric potential value. In the case of a uniform electric field, these surfaces are represented by a series of parallel planes that are oriented perpendicular to the electric field lines. Because the potential is the same everywhere on such a surface, the potential difference between any 2 points on that plane is 0. As a result, the electric field does no work on a charged particle as long as it moves strictly along an equipotential surface. You can see this visualized here as blue planes labeled with specific voltages like 9 volts or 8 volts. To put these concepts into practice, let us look at a parallel plate capacitor. In this example, A 12-volt battery is connected to two parallel plates, separated by a distance d of 0.30 centimeters. To find the magnitude of the uniform electric field established between these plates, we rearrange our formula to E equals the absolute value of the potential difference divided by the distance. By converting the separation to meters, we calculate an electric field magnitude of 4.0 times 10 to the third volts per meter. This demonstrates how a known voltage and physical spacing directly determine the strength of the resulting electric field. Next, let us analyze the motion of a proton released from rest in a uniform field of 8.0 times 10 to the fourth volts per meter. As the proton moves a distance of 0.50 meters in the direction of the field, we can use the law of conservation of energy for an isolated system. The change in kinetic energy plus the change in potential energy must equal 0. By substituting our potential difference formula into the energy equation, we can solve for the final velocity, v. Using the charge of a proton, its mass of 1.67 times 10 to the negative 27th kilograms, and the field parameters, we find the proton reaches a speed of 2.8 times 10 to the 6th meters per second. To summarize what we have covered, remember that in a uniform electric field, the potential difference is simply negative ed when the displacement is parallel to the field. We have established that electric field lines always point from regions of higher potential to lower potential. The behavior of potential energy depends on the sign of the charge. It decreases for positive charges moving with the field and increases for negative charges. We also defined equipotential surfaces as planes perpendicular to the field lines where no work is performed. Finally, we saw that conservation of mechanical energy is a powerful tool for predicting the speed of charged particles in these fields. To reinforce your understanding, consider these two review questions. First, if a negatively charged particle is released from rest in a uniform field, in which direction will it move relative to the field lines, and how will the system's potential energy change? Think about how the negative charge interacts compared to the positive proton we discussed. Second, use the dot product definition of potential difference to prove that the potential difference between any two points on a plane perpendicular to a uniform field must be 0. This involves looking at the angle between the field vector and the displacement vector on that plane.